This is Triggerflow, Trigger-based Orchestration of Serverless Workflows. And this is a collaboration between IBM Research and Universitat Rovira i Virgili. This work has been partially funded by the Cloud Button European Research Project. In this project, we are working on serverless data analytic platforms so that we want to orchestrate big data pipelines. And this is the objective of this work. First of all, let's define what is serverless. According to this IBM definition, serverless computing is a platform that's hiding server usage from developers and runs code on demand, automatically scaled and built only for the time the code is running. This definition is important because we want to comply with it for our serverless orchestrators. Look at this picture that shows the typical life cycle of an application, of a serverless function. A user uploads a file to an object store. This generates an event that goes to the cloud event bus. And then a trigger will launch a function with the action that has to be executed. This is following the classical event condition action pattern. And we must outline that this successful pattern has been extensively used in many cloud providers. In fact, event-based architectures are the centerpiece now of many cloud architectures, because they really sustain the entire feedback loop of applications, from observability using these events, analysis of these events, and interception or improvement of the application. In fact, all providers are investing heavily in their event-based architectures. All of them offer a set of built-in triggers for their cloud services, and these lists are constantly growing. I also want to outline two recent services, Amazon Event Bridge and Azure Event Grid. They are serverless event routers that provide new capabilities for creating custom event sources, but also to create new filtering capabilities or roles to redirect events to target services in their clouds. So we see the importance of this kind of event-based architectures in the cloud. Very related with that is serverless orchestrator. When we want to move an application to the cloud, it is important to have tools that can support this transition. So if we have, for example, an application that has to represent a sequence or a pipeline of functions, or a workflow where we have conditions or foregoing parallel synchronization, we want to be able to represent that in these serverless orchestration systems. We outline three of them: Amazon Step Functions, Azure Durable Functions, and IBM Function Composer. The reality is that they are not massively used, and they are not appropriate for many kinds of services. In particular, for parallel workloads like big data pipelines, they impose very important overheads that we have demonstrated in previous works. Even recent advances like Amazon Express Functions or Composer support for map and parallel jobs are only aimed for very short running functions that are not very appropriate for many long running, even minutes, big data pipelines. The consequence is that many people is implementing their own orchestrators like Pyrem, where they are blocking to wait for the finalization of some functions. But this is not clearly reactive, event-based, and serverless. So the goal of this paper is to overcome these problems. The hypothesis of this paper is that there are two main problems that we want to solve. Existing serverless orchestrator systems do not support these highly parallel foreground workloads. And on the other hand, there is a lack of extensibility and advanced event routing capabilities to be able to create new orchestrators for custom problems. For that reason, we are proposing a new extensible event-based control plane for reactive applications. This is not a new orchestration service. I really want to outline that. This is a meta tool to create new schedulers. So we want to support heterogeneous workflows, be serverless in design, comply with this requirement, have performance for big data pipelines, and provide observability and interception. This is a diagram of the Triggerflow architecture. we follow the classical event condition action model, but in our approach, all of them are extensible. We can create new event sources. We can program new conditions here, like containers, and we can, of course, program new actions with different serverless technologies. We are also offering a shared context for stateful filters, like aggregate filters that have to count events. Finally, we are offering a very simple API where it's possible to create workflows that maintain the ID in all the sequence of actions and events, and then create event sources, creating triggers, accessing the context. And we demonstrate that on top of this very simple API, we can create on top of it different kind of orchestrators. Like, for example, DAGs, step functions, or workflows as code. We have implemented 3 prototypes of the system. And the prototypes have been implemented on top of Knative event routing technologies. This works from CNCF, enabled to have like a standard for cloud events, extensible event sources, and a broker with basic filtering capabilities and triggering capabilities. It's still a young project with only exact match filtering, but it can really sustain, and we can extend it to cover the advanced routing mechanisms that we need for our serverless orchestrator service. We have now 2 prototypes of Triggerflow, one on top of Knative Eventing, one on top of KIDA. KIDA is a more lightweight project. It's using pool-based auto-scaling, but it's offering less fault tolerance than Knative Eventing. So in this prototype, we have to implement the required fault tolerance to restart workers and relaunch events, and to guarantee the at least once delivery fault tolerance model. Knative, on the other hand, is push-based. It offers fault tolerance to us, so we have less work to do, but still it has limitations on performance for some critical high-performance workflows. Once we have this architecture, we have to demonstrate that we can compile different workflows to triggers in the system with our simple API. The simple example is a sequential workflow where we have a function that when it terminates, it generates some event that a trigger would capture to generate and to launch the next function. It is very easy to understand that a DAG with a pipeline can be converted very easily using these termination events. For parallel workflows, then the only thing that we have to add here is a special trigger that is the aggregation filter trigger that will detect that all functions finished to launch the next step in the DAG. Finally, we are also supporting nested workflows, where inside a system, a workflow, we can have a sub-workflow and have a termination event for this sub-workflow. Thanks to this compile to trigger, we have demonstrated in the paper that we can now model both Amazon step functions, including nested workflows, and Apache Airflow Python-like direct acyclic graphs. So we compile these triggers and we can recreate the original workflow as modeled in these systems. But I want really to make more emphasis and more focus on workflows as code in external orchestrators, because it's more complex. So here we have a parent code where we have some steps where we call some function and then some map. And of course, we want to launch this code, but we don't want to block in these calls. So we want to suspend the orchestrator when functions are executing, because they can take minutes. So if I execute this code, I will benefit from this dynamic triggering. So as you see now, we invoke asynchronously, we add the trigger, and then we can suspend the function. And then only when the termination event arrives, the trigger will detect that, and using event sourcing, will relaunch this orchestration code. And event sourcing will catch up and will take us to the point that we arrive. And the event store will help us to recover the previous state and move to the next phase. In this case, if it is a map, again, we add a dynamic trigger, we invoke all functions in parallel, and we suspend again until the aggregation trigger will detect the termination of all events, and we can continue, use event sourcing, and finish this workflow. Okay, let's go to the validation. First of all, we want to demonstrate that we can sustain these high intensive workloads. So here you see in the table that for different computational resources, different cores, we submit a lot of events. And then some events are no OP here, or some of them are for joins. And with this synthetic workload, we demonstrate that we can sustain a lot of events per second that are enough for our big data pipelines where we have thousands of functions in parallel. We also demonstrate that the resource utilization is efficient and constant depending on the number of events that we inject to the service. Another thing that we want to demonstrate is that our overhead is comparable to public cloud service and even better for parallel workloads. So here we are showing sequential and parallel workloads, and we compare against Amazon Step Functions Express, Step Functions, IBM Composer, and Azure Durable Functions. And we see we don't want to beat them. We want to demonstrate that we have comparable overheads. Of course, in sequential ones, we have a small penalty over the official services because they are natively implemented and integrated with their cores. We are an external service. But for parallel workloads, we see that our system scales better than the other as we increase the number of parallel functions. Finally, we want to demonstrate that our system complies with this serverless definition. First, it's auto-scalable. Here, we inject some scientific workloads that are auto-scalable, and the system is adapting transparently to the system. Then we demonstrate fault tolerance. We suspend the worker, and we can see in this scientific geospatial realistic workload that we recover in that moment, and we continue from that point perfectly. And finally, observability and interception. We can transparently intercept triggers to, for example, do a pre-warming before a map. And we observe that then we are more efficient in some workflows that need this interactive speed. So we have demonstrated that our system supports different workflows, that it complies with the serverless definition, and that has comparable overheads to public clouds. The conclusion is that Triggerflow is an extensible control plane for reactive applications. It is serverless, according to this definition. It is extensible. We demonstrated that you can build different kinds of services on top of it. It supports highly parallel workflows with good performance, and it builds on open source technologies. It is here available for any user to extend it or to compare with it. There are some limitations, of course, to this system. Knative Eventing is a young and evolving project with some performance limitations and very restricted filtering capabilities, but it's moving on. Kida is promising, and they are even talking about integration with Knative Eventing. Portability across clouds, it's not yet available. When we have multi-tenant Knative systems with Knative Eventing, this could be very interesting to compare systems across clouds. And finally, there are limitations in observability in unintegrated cloud event architectures. But the conclusion is that this event-based, trigger-based orchestration of workflows has a lot of potential for many applications in the cloud in the next years.